So thank you, everybody. Welcome. Looks like we have a few people still trickling in, but we're going to get started. This is our April 2021 talk. We are, of course, really looking forward to getting back to being in person, but that probably won't be till this fall. With everybody traveling and everything, it's nice to kind of keep things virtual for the summer, and so we'll probably do that anyway, and we might keep that venue going in future summers when we tend to get a little bit quiet and people are not necessarily in the heat of lovely Tucson, Arizona. So anyway, if you don't know me, I'm Jonathan Whittier, this year's chapter president, and thank you to Mike for reaching out to Chelsea. And thank you, Chelsea, for agreeing on such short notice to give your talk tonight. I think it's really exciting in our backyard. So I don't know if any geologist in Tucson and in Arizona who's not familiar with the area at least. So hopefully this is some added information for them. And short little introduction that Mike put together is Chelsea received her PhD at Arizona State University School of Earth and Space Exploration in 2018. Her dissertation was highly explosive mafic volcanism, the role of volatiles. And while at ASU, she was part of Amanda Clark's volcanic research team. And after graduating, Chelsea joined Cornell's Earth and Atmospheric Department as a visiting lecturer, and has since moved to Baylor University as a postdoc research associate, and has built an impressive string of publications with collaborators Amanda Clark, Kurt Roggensack at ASU, Michael Ort at NAU, I'm going to say this wrong, Fabrizio Alfano at ASU, Stephen Self, and Sarah Hansen at Adrian College. So if there's anything else you'd like to add, Chelsea, otherwise, welcome and thank you for this again, and go ahead and get started. Oh, quick note, everybody, if you haven't already, or if Mike hasn't muted you, please mute your microphones. Thank you.
All right. Well, thank you so much for having me. I'm very excited to talk to some fellow Arizona geologists about Arizona geology. I'm sorry, 1 second. Okay, there we go. Oops. Sorry, all this screen sharing business. Have to get organized. Okay. So I'm going to talk today about the eruption of Sunset Crater volcano, which probably most of you are very familiar with. You've at least been there, I would imagine. And this eruption was a really strange eruption. It was very large, and it's just this small scoriocone volcano, and that's very unexpected behavior from this type of volcano. So what I did for part of my PhD is I used teeny tiny crystals, and I looked at inclusions inside of those teeny tiny crystals to try and understand what was going on to generate this really explosive eruption at Sunset Crater. And since Sunset Crater erupted before the time of modern photography, I don't have a nice photo of the eruption for you, but I do have this, this image from Pericotin volcano in Mexico, which erupted in the 1940s. And this was also an anomalously large scoriocone eruption, but it was larger in volume than Sunset, but it was actually less explosive than Sunset. So this picture can maybe give you a sense of what it might have looked like at the time when Sunset was erupting, but it was actually probably even larger than what this picture shows. And so before I move on, I'll just point out, if you are viewing this in full screen and need a space for the video, I'm leaving that top left corner open for you through the whole talk. Oops, sorry. Okay. So Sunset Crater is a mafic volcano, and mafic volcanism is really diverse. So I have a few videos here to show you about mafic volcanism. So some of the more typical activity that erupts from mafic volcanoes are these effusive lava flows, which are shown here in this time-lapse video from Iceland, which is erupting today and has been erupting for the past month. And you know, if I was giving this talk 3 or 4 years ago, I probably would have shown you a beautiful video from Kilauea's Pu'u'au, which was erupting for 35 years. But now, of course, we have new examples. So some other really typical activity at mafic volcanoes are these small strombolian eruptions. seen here at Etna. And so, of course, Etna is also doing some interesting eruptive activity today, but this is kind of the more typical activity that you would expect from this video from a few years back. And what we think is happening at strombolian eruptions is that you have these large bubbles coming up to the surface and bursting and tearing the magma apart. And so again, this is really typical activity at mafic volcanoes. But you can actually get some highly explosive eruptions happening as we saw at sunset. And so this video is a more recent eruption from Stromboli volcano in Italy. And this was in July 2019. And so this eruption it was clearly large and explosive, but again, nowhere near the magnitude that we're talking about with Sunset Crater. And in fact, there have been even larger eruptions than what occurred at sunset. So we actually have Plinian eruptions in recorded history, or not in recorded history, but in Earth's history. So specifically, like at Etna, there's one dated at 122 BC that was highly explosive. So how do we explain these mafic explosive eruptions? So the diagram that I've plotted here is kind of a typical way to classify different styles of volcanism. So over on the left, we have kind of less explosive activity in basaltic magmas. And then in the right, we have more silicic magmas. And in the top, we have the most explosive, which are the sub-Plinian to Plinian eruptions. And so generally, how do we make a really explosive eruption? Well, you need to have your magma brittly fragment. So that's represented by that orange line on the plot there. And so, of course, then the next question is, well, what controls fragmentation? And so generally, it's controlled by the viscosity of your magma, which is what's shown on the x-axis here, and then your strain rate, which on the y-axis, it's plotted ascent velocity. And so strain rate can kind of be considered proportional to the ascent velocity. And so basically what I'm telling you is that basaltic magmas over on the left should not be behaving in this sub-Plinian manner. And so that's kind of the driving question of this whole talk and part of my PhD research, which is how did Sunset Crater, this mafic or basaltic magma, produce this large sub-Plinian eruption? So the reality is that, of course, the simple diagram can't explain all eruptive behavior. So there are a lot of different factors that go into this. So the melt composition is one thing that strongly controls the viscosity of the magma. But also, your magma forms, and then before it erupts, it can undergo a lot of different changes. So it can change in temperature and pressure, and that can cause crystallization of your magma. And it can also cause volatile exsolution, so you can have bubbles in your magma. And then, of course, there are some external factors that can impact your eruption. Things like the geometry of your conduit, what the magma is erupting through, can also impact that. And so in today's talk, I'm going to focus in a good amount of detail about volatile exsolution and how bubbles can impact the explosivity of an eruption. So now I will take you to beautiful Sunset Crater. So we'll start with a wide view. So Sunset Crater is shown in the blue marker here in the satellite image from Google Earth. And it's the youngest eruption in northern Arizona's San Francisco volcanic field. And as you can see from the satellite image, we have our beautiful basin and range topography kind of surrounding the whole western part of this image. And then Sunset Crater is kind of right on this edge, this boundary that's clear in the image. And of course, this is the Colorado Plateau. And so the San Francisco volcanic field is right on the rim of the Colorado Plateau, as well as a number of other volcanic fields. So all of these gray blobs in this map are other volcanic fields. And so most likely the melting in this region is in some way related to this boundary between the Colorado Plateau and the surrounding geography. So if we zoom in even further, here's an elevation map of the San Francisco volcanic field. And what you can see is there are tons and tons of vents here. So just a bunch of these tiny little pimples on Earth's surface, these tiny cinder cone volcanoes. And in fact, there are over 600 in this volcanic field. But this volcanic field also has a few silicic centers, some of these higher topography regions that you can see in this image. And this field has been active for the past 6 million years. And Sunset Crater is, again, the youngest eruption. It's in the eastern part of the field, but it's not the furthest east eruption. So the activity has kind of generally moved from west to east, but it's not a perfect relationship. So here is our beautiful Sunset Crater with its nice oxidized red rim, which gives its name as Sunset. And so again, it's a small scoria cone volcano up in northern Arizona. It was protected as a national monument in 1930 because Hollywood wanted to blow it up for a movie. And we wisely said, no, let's not do that. Let's keep it safe. And this eruption occurred about 1,000 years ago. The current knowledge on the date is about 1085 for the eruption. And there were native people living in the area at the time that it erupted. So this image here shows some ruins from Wupatki National Monument, which is a little bit north of the volcano. And so there were native people living there who were experiencing the eruption, but also years after the eruption, it was really interesting that the cinders from the eruption actually helped the people who were living there, and it kept moisture in the ground, and so that allowed Wupatki to become a bustling center at that time. So if we zoom out a little bit further, again, this is a satellite image again from Google Earth. So you can spot sunset really clearly by, again, its bright red rim. And what you can see is that there's all of this black material immediately surrounding it. And this is all material from this eruption. So it's a very large volume eruption. It was about half a cubic kilometer that erupted. And as it turns out, if you map this deposit and go into the details, this was a sub-Plinian event, one of these really highly explosive eruptions. So this isopack map here by Michael Ort, it shows how far the tephra was dispersed from the vent. And so those isopacks that are shown there are in centimeters. So you can see that the tephra was dispersed over 25 kilometers from the vent. And that's a 10 centimeter isopack. So 10 centimeters thick of tephra over 25 kilometers from the vent. So this was huge eruption. And that corresponds with eruption plumes that are over 20 kilometers high. So they're up into Earth's stratosphere, just this really massive eruption. And again, this is really unexpected behavior for a scoria cone. So I'll just quickly walk you through what we think happened in the Sunset Crater eruption. And there were kind of three main eruptive phases. So at first, there was a small fissure eruption. So you had a couple of lava flows and a very thin layer of tephra that was deposited. And then activity quickly centralized to the main vent where Sunset Crater is today. And at this point, the two large lava flows began to erupt, and another layer of tephra was deposited. And this tephra is very obvious in the field because it's completely oxidized. So it's this very red unit. And then the main part of the eruption was this sub-Plinian phase at the main vent. So these two lava flows were continuing to erupt at the same time, but then also you had these three massive eruptions of tephra, these explosions. So, and this is where we get these really high eruption plumes, 20 kilometers high. And then finally, as the eruption faded out, we had some waning activity, a few discrete tephra layers were deposited, and eventually the lava flow shut off. And so overall, we think that probably most of this eruption occurred in about a year, probably not longer than a couple of years at most. So it's happened really quickly. And I'm mostly going to be focusing on unit 3 here, this tephra. And so again, this is the most explosive part of the eruption that I'll be talking about. So again, I'm going to use crystals to try and understand what happened at this volcano. And again, I want to know, why did this Mafic volcano erupt very explosively in this sub-Plinian eruption. And in particular, I'm really interested in volatiles in the magma. So this work was recently published in Nature Communications earlier this year. So if you want to know things in more detail, you can ask me later or read the paper. So again, we go out into the field and we collect tephra from this eruption. So again, I'm focused on unit 3. So, we dig the holes, we gather the tephra into bags and take it back to the lab. But there's kind of a problem here, which is that, of course, as magma ascends, volatiles exsolve from the magma because it's depressurizing. And so this tephra that you bring back doesn't have the original dissolved volatiles in it. All of that, went up into the atmosphere. So this is where the crystals come in. So these crystals are free crystals in that tephra deposit. And we can study inclusions trapped inside of these teeny tiny crystals to help us understand what's happening in the subsurface. So these melt inclusions look like these pictures over on the right. And these melt inclusions get trapped inside of the crystals as they grow at depth. And we specifically use olivine because olivine is it's the first mineral to crystallize from the basaltic magma. So it tells us what's happening at the deepest part of the plumbing system. And what's really great about this is that the crystals serve as a pressure vessel. And so the volatiles stay dissolved in these melt inclusions, whereas in the rest of the magma, the volatiles dissolve as it erupts. And so you can see here, I've labeled the olivine crystal and then the melt inclusion, which again, once it quenches, it becomes glass. And of course, like anything in science, it's not quite this easy. So there's also a bubble inside of these melt inclusions. And so that's going to be one of the main things in our story today. So it turns out that these bubbles really matter a lot. So how do these bubbles form, first of all? So the melt inclusions are trapped as a little pocket of melt in the crystal. But then before the crystal erupts, some things can happen. So you get two processes that occur as the temperature drops in the magma. So first, you can have shrinkage to produce a bubble. So as soon as your temperature drops a little bit, both the crystal and the melt inclusion shrink. But because of the differences in thermal expansivities of these materials, the melt shrinks more. And so then you're left with this void space that becomes the bubble. And you can also get post-entrapment crystallization along the rim of the melt inclusion. So again, as soon as the temperature drops, that means that the melt wants to crystallize more. And so it crystallizes this little ring of olivine along the edge of the melt inclusion. And again, you're losing volume because you're going from liquid to solid, and that creates a void that again becomes your bubble. And so in recent years, in kind of the past 5 or 6 years or so, there's been a number of studies in these melt inclusion bubbles. And these studies have found that up to 90% of the total CO2 in your melt inclusion is actually in the bubble. And so this, drastically changes the interpretation of an eruption. And so the reason why CO2 is mostly in the bubble is because the solubility of CO2 in magmas is really strongly pressure dependent. So as soon as you drop the pressure in the melt inclusion a little bit, the CO2 exalts into the bubble. And so this means that we have to measure the bubble CO2. And so in my study, we did this using Raman spectroscopy. And so just to kind of give you a visual of what this might mean in this plot here of water and CO2 contents. So if you had a melt inclusion where you only analyze the glass phase, you might have 1,000 ppm of CO2. But if you analyze both the glass and the bubble, you might have something like 4,500 ppm of CO2. So the curves that are drawn on this plot here are fluid saturated isobars. So they're correlating the volatile contents with pressure. And so again, if you didn't measure the bubble, you might think that your magma was stored much more shallowly than it actually was. So at Sunset Crater, when we analyze these melt inclusions and their bubbles, the first thing that we know is that, or the first thing that we notice from this data is that we have two different groups of melt inclusions. And this is mainly classified based on the CO2 data, which I'll show you in just a moment. But basically what we see is that larger bubbles seem to be different than smaller bubbles. So for the rest of the talk, I'll label the melt inclusions if they have these smaller bubbles, less than 2.5 volume% in size. I'll have them filled in as black symbols. And then the group 2 bubbles, these larger bubbles, larger than 2.5 volume%, I'll leave them open. And so, of course, the first question might be, well, okay, maybe there's some magma mixing or something happening. And so maybe these melt inclusions come from 2 different magmas. But that is not the case here. So this plot here is showing you the total alkali content, so your total sodium and potassium, compared with your total silica content of the melt inclusion. And the curves and the classification here, this is just how we classify different magmas. And so again, all of the melt inclusions kind of plot in this small range. They're all this alkali basalt magma. So it's the same magma, and yet we have 2 different groups. So here is some of the CO2 data. So this is the total CO2 content of the melt inclusion, so the glass and the bubble, and then compared with the force-strike content of the crystal that it's hosted in. And so the force-strike content tells us it's kind of a proxy for crystallization. So as the magma continues to crystallize, you get lower and lower force-strike contents. And so the first thing that I want you to notice on this plot is that the 2 groups they're trapped in the same olivine crystals. So there's not, it's not like the group 1 were in lower force-strike and the group 2 are in higher force-strike. No, like they all overlap in force-strike content. So again, we don't think that these 2 groups are at all related to any kind of crystallization in the magma. But again, the main conclusion here is that the group 2 melt inclusions, the ones with larger bubbles, have more CO2 in them. And so that's weird. Why is that happening? Well, before I move on to why might that be happening, I do want to point out one other thing from that plot that I just showed you. Which is that plot was showing that CO2 content is actually changing with your force-strike content of your crystal host. And so the first thing that you need to know is CO2 is incompatible in olivine. So as your force-strike content gets lower, you're not incorporating any CO2 into that force-strike, so it's staying dissolved in the melt. And so we kind of have to ask ourselves a question then, is the behavior of CO2 with crystallization is going to depend on whether your magma is volatile saturated. So this is just kind of a schematic diagram here, but it's the same axes as that last plot that I showed you. So if your magma is undersaturated in CO2, then as crystallization occurs, you're just going to concentrate your CO2 in the melt. And so your CO2 content should be getting higher. But if you are at volatile saturation, then your CO2 is going to be concentrating in the melt, but it will no longer be soluble in that melt. And that means that the melt becomes supersaturated, and then CO2 has to exsolve into a bubble. And so if we look at the sunset data again here, we see that we do have this CO2 saturated trend, where as we crystallize the magma, we have less CO2 being trapped in the melt. And so this means that this crystallization is occurring in a bubbly magma. But again, we still have these 2 trends. So both of these trends are CO2 saturated trends, but one is offset from the other at higher CO2 contents. And so really one of the only explanations that makes any sense here is that these bubbles must be forming by different mechanisms. And so this is a hypothesis that we can test. And so how can we explain this? Well, we can actually model these bubble growth processes that I mentioned earlier, the shrinkage and post-entrapment crystallization. We can model that to see how large a bubble can grow in a specific sample. And so that's what I'm going to be showing you on this plot here, which is showing the bubble volume percent compared with this change in temperature. So it's the change in temperature between when the melt inclusion was trapped and then right before it erupts. And so we have 2 stages of bubble growth. So our inclusion changes a little bit before it erupts and then also after it erupts. So before it erupts, you have both of those 2 processes happening. So you have both shrinkage and post-entrapment crystallization going on that we have to account for. And this is kind of, this is accounted for in this diagram by the x-axis. So this delta T is calculated based on the amount of post-entrapment crystallization that has occurred in the sample. And then stage 2 is after the melt inclusion erupts and as it's cooling. And this is represented on the plot by this line here, and which is labeled TG for the glass transition temperature. So when, the temperature at which the melt turns into a glass. And we determine this TG based on how quickly the magma is cooling when it erupts. And so during this late stage growth, we only have shrinkage happening because this cooling is really, really rapid, right? It's a sub-Plinian eruption. It's shooting out of the ground very, very rapidly. And so we don't have any post-entrapment crystallization happening. And so if I plot the data on this diagram for you, again, the curve shows you the maximum bubble volume that you can get from this eruption. And so what you can see very clearly is that the group 1 bubbles, those smaller bubbles, they make sense in this diagram, whereas the group 2 bubbles, the larger bubbles, they plot above this maximum bubble volume. And so kind of the only explanation that makes sense is that this must mean that these group 2 samples were trapped as both melt and a bubble when they formed. So you had a bubbly magma when the melt inclusion was trapped. And so I'll just kind of walk you through this quickly, like what this would look like as the magma's erupting. So when the melt inclusions first are forming during crystallization, you have 3 types of crystals. So you have some crystals that don't have any melt inclusions in them. You have some that trap just melt, and then you have others that trap both melt and a bubble. And then again, before it erupts, as it's undergoing this pre-eruptive shrinkage and post-entrapment crystallization, you have a little bit of bubble growth. So in group 1, you have a bubble forming and growing, and then in group 2, you just have the bubble that already exists growing a little bit. And then as it erupts, it only shrinks, but again, that still leads to some bubble growth. And so both of those bubbles continue to grow a little bit more. And so what this ends up with is that then you can get these larger bubbles in your group 2 melt inclusions. All right, so we think that we have a mechanism for explaining why these samples look the way they do, but now let's actually look at the data that we can get from these samples. So here I'm showing you the dissolved volatile contents when the melt inclusions were trapped. So what was actually dissolved in the melt when they formed. So I'm excluding from this plot any bubbles that existed at the time. So for the group 2 melt inclusions here, I'm showing them in cyan instead of, previously I'd just left them empty. But this is just representing that I'm not including all of their CO2 here because again, we think that they had a pre-existing bubble. And so what you can see is that we have really high CO2 contents. And again, the isobars that are plotted here, these are fluid saturated isobars that are specifically constrained to the Sunset Crater magma. So these are from it's from experimental work that I did on Sunset Crater. And so what you can see from those isobars is that your melt inclusions are being trapped between about 300 and 500 megapascals. And so that correlates with about 12 to 17 kilometers depth. So we have our kind of nondescript magma body over here at 12 to 17 kilometers below the volcano. But something else that you can see on this plot is that the group 2 melt inclusions, again, the ones that are trapped with that bubble, they're kind of throughout the entire magma storage region. And so this suggests that the entire magma storage region is bubbly. And so we have this bubbly magma at these great depths. And these depths correlate with about the middle of the crust in this region. So again, this really deep, bubbly magma. And so what we think happened to produce the eruption is that we had continuing crystallization and accompanying exsolution of CO2. And as this continued, eventually the overpressure became too great from those CO2 bubbles, and it was able to fracture the wall rock and then lead to very rapid magma ascent that then produced the SubPlinian eruption. And so we think that the bubbles here are really key to generating this very large eruption. So we have this mechanism at this basaltic volcano. And so you may be wondering, well, has this mechanism been proposed anywhere else? And in fact, it has at a much different eruption. So we have, in silicic magmas, we can get these very, very large eruptions that produce calderas. And so one in particular, the Bishop Tuff, which produced the Long Valley caldera in California, was this massive event that may have also been driven by these exhaled volatiles in the magma chamber. So this is work from Paul Wallace's group, and what they found is that they found a lot of exhaled gas in the samples prior to eruption. So this is showing you pressure and the amount of exhaled gas, and then they're also correlating that exhaled gas with the density of the magma. But anyway, what you can see from this is that there's significant amount of exhaled gas, up to 6 weight% exhaled gas. That's just like a massive amount of gas in this eruption before it erupts. And so if we just do a quick comparison between Sunset and the Bishop Tuff, I'm not trying to imply that this is the same eruption, right? This is actually, they're completely different. So Sunset Crater is this basaltic magma. Bishop Tuff is, nice silicic rhyolite. Sunset is nothing compared to Bishop in terms of volume. Bishop is huge. The pressures that we're talking about for where the magmas are stored, Bishop's a lot shallower than Sunset. And the volatile composition is very different. So at Sunset, we have pretty low water contents, but a lot of CO2, whereas at Bishop, it's the reverse. And again, the gas composition at Bishop is also, it's mostly water, whereas at Sunset, we're talking about CO2. So again, these are very, very different systems, but they may have both erupted kind of from a similar mechanism, which is really interesting. And so this might lead you to question, well, could this be a mechanism for all basaltic subplinian eruptions? And so, well, one thing that I didn't emphasize very much is that Sunset Crater is an alkali basalt. And this is important in terms of its volatile content. So we know that basalts that have high alkali contents can actually dissolve a lot more CO2 than their low alkali counterparts. So this plot is showing you here pressure versus CO2. And you can see more of our mid-ocean rid basalts have low alkali contents and low CO2 solubilities. Whereas if you increase the alkali content, you can get orders of magnitude more CO2 dissolved in your melt. And these alkali-rich magmas include volcanoes like Etna and Stromboli, which are also known to produce some really highly explosive events. And so it very well could be key to explaining some of these basaltic subplinian eruptions. But we don't have the bubble data yet. So these are some melt inclusions from Stromboli here. And as you can see, they have bubbles in them. So we really have to get that bubble data to understand if this might be a common mechanism. But it's not the only mechanism that's been proposed. So at some other Mafic highly explosive events have been proposed to have occurred as a result of rapid crystallization of the magma. So these it's been proposed at places like Masaya and Tarawera. These were some basaltic not subplinian, Plinian eruptions, so these really massive eruptions. And so what you can see in these figures on the right here, the first thing that I want to point out is that the depths that we're talking about are much different. So this is showing you only down to 3,000 meters, whereas at Sunset, we were talking about 15 kilometers. So if there's any rapid crystallization going on, that's going to be a really shallow process. And so if you get these really rapid microlights forming, it can impact the viscosity of the magma and lead to this brittle fragmentation. And that's what's shown in these figures here. So another thing that I haven't gotten a chance to talk about yet, because I've been talking about CO2 so much, is that Sunset Crater also has really high sulfur content. And so we estimate that it emitted about 5 megatons of SO2, which is a lot of sulfur. And sulfur is really important because if you inject sulfur into the stratosphere, you can generate aerosols there. And then the aerosols scatter solar radiation back into space, which means that Earth's surface cools as a result of that. And so that's shown in this plot here. It's showing you transmission through the atmosphere by date. So sorry, I don't know if you can read all these dates here, but this is kind of 80s here. And so there are two clear eruptions that happened to alter the transmission. And so one of them is El Chichon from Mexico, and then the other is Pinatubo in the Philippines. And so those are very, very clear from this atmospheric transition standpoint. And so I don't want to lead you on too much here because there's another really important aspect of injecting sulfur into the stratosphere, which is the latitude at which it's injected. So the Pinatubo eruption, for example, is at very low latitudes, where Sunset Crater is kind of at mid latitudes. And so when you inject things in the stratosphere at low latitudes, because of circulation dynamics, that can allow it to spread across the entire globe. Whereas at sunset, we wouldn't expect impacts too far beyond where sunset is. So I'm going to show you just a couple quick examples here from Pinatubo and Tambora. So some of these low latitude volcanoes and how they impacted the climate as a result of the sulfur. So again, Pinatubo erupted in 1991 in the Philippines. It erupted a dacite magma, so much more evolved than sunset. But this eruption impacted global climate for 3 years after the eruption, which was pretty significant. And so if we compare this to sunset, Pinatubo erupted 10 times more magma, but it only released 3 times as much SO2, which is really interesting. And then Tambora, of course, in 1815 in Indonesia, this was the eruption that produced what's called the year without a summer. And this was, again, an eruption of more evolved magmas. It was a trachyandesite magma, so a high alkali andesite magma. And again, compared to sunset, this was a much larger eruption, erupted 60 times as much magma, but again, it only released 9 times as much SO2. And so this comparison might suggest that some of these modest volume basaltic eruptions could, in fact, impact the atmosphere, especially if they're at some of these lower latitudes. So that might be something to look out for in the future. All right, and then getting back closer to home again, thinking about what might happen. Could the San Francisco volcanic field produce another eruption? So the USGS considers the San Francisco volcanic field to be a moderate threat if it produces a future eruption. So they're not saying that it's going to, they're saying if it produces eruption, it could be a moderate threat. And so this threat assessment ranks all the volcanoes in the US, and the top 3, just so you're aware, are Kilauea, Mount St. Helens, and Mount Rainier. And they all have threat scores that are over 200, whereas the San Francisco volcanic field's threat score is 51. So this threat score is based off of the most recent eruption, which is, of course, Sunset Crater. But as I mentioned earlier, there are 600 other normal scoria cones in this volcanic field. And unfortunately, the score is based on things that matter in terms of the style of the eruption. So the score is based on the hazards that the eruption can produce. So like, if you can get pyroclastic flows or tsunamis or, really dangerous hazards. And it's also based on the unrest since the last eruption. And it's based on what's called exposure, so the nearby population and the infrastructure that would be impacted by a future eruption. So at least part of that score is based on hazards that would be produced by another Sunset Crater eruption, not necessarily just any eruption in the field. So our score could be a little bit different if the eruption is not as large as sunsets. So of course, that begs the question, well, could we get another sub-Plinian eruption like Sunset Crater in the San Francisco volcanic field? So I have a lot of questions here and not a lot of answers for you. But one thing that I think would be really important to know in terms of thinking about this is, do any of the more typical scoria cones in this field have high CO2 contents? So we have a number of, youngish vents in the field that are just ripe for volatile analysis on them. So, I just showed some pretty ones here. So Merriam crater, which is important in terms of planetary geology as well, because it's used as a lunar regolith analog, which is cool. And then, of course, SP crater, which you just have to put up because it has that beautiful lava flow. The truth is that we don't know anything about the volatiles in these other eruptions, and so that would kind of be step one to understanding if we might get a future eruption that's like Sunset. Another thing that we want to know is, where did the CO2 come from? So how did Sunset get such a high CO2 content? And so again, I think the answer is probably that long-lived flat subduction probably metasomatized the mantle there, and that's why you have all this juicy CO2 there to include in your magma. But again, we don't know that for sure. And unfortunately, or fortunately, but sort of unclear, there's a lot of variability in the magmas in the San Francisco volcanic field. So again, this here is our total alkali versus silica diagram. And this is showing you a bunch of different vents from the San Francisco volcanic field. And so this was data that was collected by the USGS and compiled in this great paper from Arculus and Gust. And you can see there's tons of compositional variability. And this Arculus and Gust paper concludes that there's variable degrees of partial melting that's forming these magmas, and there are different sources that they're melting from, and there's also mixing of different components in the source. So there's a lot of variability, and so we wouldn't necessarily expect the magma to be identical to Sunset Crater in the future. So just to kind of wrap up everything I've talked about so far, so we have this 1,000-year-old eruption of Sunset Crater, which was a sub-Plinian eruption, this really large eruption. It's erupted right on the edge of Colorado Plateau, which probably has something to do with why it even erupted there, why magma production is happening there. But again, it's in this field with 600 other kind of normal scoria cones. And so my research suggests that this really explosive eruption was driven by bubbly magma that then fractured the wall rock and drove rapid magma ascent, causing this sub-Plinian eruption. And it's very possible that this mechanism is something that could happen at other mafic volcanoes, especially if they're alkali rich and they have that increased CO2 solubility. So they have more CO2 to start with, which can generate more CO2 bubbles. And this eruption had produced a significant volatile output. So it had, a lot of CO2. It also had a lot of sulfur, which is very important. But of course, it wasn't at a tropical latitude, so it probably didn't have the same impact that something at the equator might have. And then, of course, can we get a similar eruption in the San Francisco volcanic field in the future? I wish I could answer that question for you, but we'll have to do more research. So anyway. All right, and that's all that I have for you guys today. So I'm happy to take questions.
Wow, thank you, Chelsea. That was great. There are some questions from the chat room. Do you have access to that? Can you see those? Do you want me to?
Do I? That's a good question. Hold on. There we go. Okay. Here's the chat. Okay. Any idea how long the phase 2, the sub-Plinian eruption lasted? I don't have a good answer for that. So
how about the phase 3, the sub-Plinian phase? Do you have any sense at all? Was that a very, very short?
Yeah, I'm not sure. Okay. Yeah, we think like the total eruption is probably less than a year. It was probably kind of, maybe you had eruptions over a couple of days, and then you had pauses for days to weeks to maybe even months before something else happened, because we do see these distinct layers in the field. Right, so then the next question is about the source of CO2, which I covered later. So we don't think that it's the limestone, because this is at such great depths. So, and the limestone's a little bit shallower. But it's within the realm of possibility, but I think that we might see some different trends if it was based on incorporation of the limestone, the wall rock, because that's one of the reasons why there are some of these more evolved vents in the San Francisco volcanic field is most likely from incorporation of the crust. Another question is there any independent evidence for the depth of the magma chamber? So that's a great question. Our collaborators at NAU, Ryan Porter, was doing some geophysics, trying to get some imaging done. And so I think that data is kind of still in limbo a little bit. So there was maybe some evidence at something like 12 kilometers for maybe something different happening in the crust. So possibly. Okay, next question is about in Springerville, White Mountain volcanic field. It's a large amount of CO2 in the subsurface at fairly shallow levels today. Little available isotope work suggests a magmatic source, possibly the mantle. And so is there any subsurface CO2 near Sunset? Not to my knowledge, but it might just be that we haven't looked for it. So yeah, I'd be very interested. I need to look up that paper on Springerville. That sounds really interesting.
Yeah, that's the CO2 at Springerville, and the individual can correct me if I'm wrong. I believe it's hosted in fractured granites there. They were at one time there was some thought about tapping into the CO2 and then sending it to the oil fields in Texas. That didn't come out. Chelsea, these with fraction or with fragmentation occurring at 12 to 17 kilometers, do you see xenoliths from the middle crust in the Sunset fallout?
So in the fallout, I don't know that I've seen it. So we don't think that the fragmentation is, well, I guess, yeah. So we're fragmenting the wall rock. Sorry, I'm thinking of fragmentation of the magma, which is of course happening much more shallowly. Sure. But yeah, there are crustal xenoliths in the lava flows, I know. So there are a number that you can see, on that path through the Benito.
Yeah, they're mostly Cuyabab and I think maybe Coconino, the ones that I've seen. So they're not coming from very deep.
Right. Yeah. So I'm not sure. I don't know that we've seen anything from greater depths than that.
Okay. Are there other questions? People can probably, if you feel like you want to throw out a question, please feel free to unmute yourself and address Chelsea directly. You should be able to unmute yourself.
Yeah, I think there was one more question that appeared in the chat, which was, is volcanism at Sunset Crater and San Francisco Peaks related? So, I mean, not directly, not temporally, not in time. But of course, it's in the same volcanic field. So it's all from some similar source of melting. And as I said, there's a lot of variability in the melting. So again, they think that the silicic centers are mostly became silicic as a result of incorporation of the crust there.
It might be worth noting, and people can argue about this, is the Uinkaret volcanic field on the north rim is potentially more hazardous because it could dump basaltic lavas down into the canyon, blocking the Colorado River.
Yeah, that would be wild.
That would be wild. Are there any other questions for Chelsea? I guess not. So maybe we should, John, do you want to call it a day?
Sure. Oh, that's very nice, Chelsea. Thank you so much. That was really fascinating stuff.
Yeah, you're welcome. Yeah, I hope, I'd love to hear from people if more questions come up afterwards. Please send me an email. Love to talk about Sunset with other people. And yeah, hopefully I've given you a little perspective on the volcano in your backyard.
Chelsea, I have one other question for you. Is I don't think of these little cinder cones as having magma chambers per se. They must have a very different appearance than the larger silicic centers, which have massive magma chambers. I mean, do you have a picture in your mind of what basaltic magma chamber for something like Sunset looks like?
Yeah, that's a great question. And I think we really know so little about these basaltic systems, aside from the ones at like Stromboli and Etna, for example, where these long-lived and, much more massive volcanoes, because again, it's this short-lived magma, right? It can't be stored in the crust for too long of a time or it'll just all crystallize and, it's not going to erupt. So yeah, the question is, how do you store this much volume, the volume that erupted at Sunset, right? So, you of course, probably had at least 4 times, if not much more magma, at depth than what erupted. And so you had to have a lot of magma. And it's all compositionally, it's the same stuff. So even throughout the different units, throughout all those different tephras, it's all the same magma. It's compositionally like exactly the same. And so that's kind of amazing. And so, yeah, you wonder, is it kind of a larger body that's, of course, it's not like the cartoon that I drew, that's just a cartoon.
Right.
Is it like a series of different dikes and sills or what? Yeah, we just don't know.
Okay.
Interesting. There is one more question. I think you alluded to this a little bit, but maybe you can go into more detail. But was there a direct impact on the local population at the time?
Yeah, so I'm certainly not the best person to answer this question, but I can refer you to Michael Ort at NAU. He's done a lot of work with the archaeologists on this, and so yes, there certainly was. So there were people living in the area. There's evidence of corn sacrifices in the lava flows, and then of course the entire sediment of Wupatki. So of course people were displaced when the volcano was erupting, and then years after the eruption, the cinders were actually protecting the ground and allowing the ground to retain its moisture. And so that allowed Wupatki to be this like bustling agricultural center as a direct result of the eruption, which is pretty cool.
Yeah, it really is. I wouldn't have thought of that as a product.
Yes, well, you see that. So, I've been working in the Canary Islands recently, and they grow wine in their cinder cones there because the cinders they can like protect it with this little like crater of cinders, which is cool.
Yeah.
So they actually build little cinder cones around each plant.
Yeah, well, so they just like they have these little they like make these tiny little bowls of the tephra.
I think it's the same idea along the idea of mulch. They're basically mulching with cinders, which is keeping the water in the soil for a little longer than it would normally stay there.
Mm-hmm. Yeah, that makes sense.
Chelsea, thank you so much. And John and everybody, we are having next week, or excuse me, on the 4th of May, Ryan Crow from the United States Geological Survey is going to be talking about the opening and the origin and the evolution of the lower Colorado River. So Chelsea, join us for that.
Yeah.
Great. Well, yeah, thanks again for having me. This was super fun.
Yeah,
okay.
Definitely. And if you don't mind, Chelsea, when Mike posts this, maybe he can post your email address and people can follow up with you if they have more questions, as you said.
Yeah, for sure. Yeah, my email is on the first slide also. So
yeah,
perfect.
We'll do.
Great. Thank you so much. This was great.
Great. Thanks so much.
Thanks a
Have
lot,
a great
Chelsea.
evening, Al.
Okay, take care. Bye-bye.